for certain large nuclei, they tend to be in the bottom part of the periodic table. You can get nuclei which can split. So what happens is you've got a large nuclei, and you'll remember that the example that we always tend to come across is uranium-235. So that's uranium, mass number 235, atomic number 92. And this splits into two daughter nuclei, two fragments, and then usually 2 or 3 neutrons are also produced. Now, as it turns out, for many nuclei, or for quite a few nuclei, that can happen spontaneously. But at IGCSE, we're interested in a type of fission called induced fission, whereby we stimulate the process by making the fissile nucleus absorb a neutron. So the uranium-235 absorbs a neutron and then splits into two daughter nuclei, which can be, as long as the mass number and the atomic numbers add up to what uranium has, there are a range of different pairs of daughter nuclei that can be produced, but you don't need to worry about that. So daughter nuclei. And these neutrons here, which are produced, are very important, because if you have a sample containing many uranium-235 nuclei, you then get fission occurring, producing neutrons, which then cause more fission, which then produce more neutrons, which then cause more fission. So we know that as a chain reaction. So a chain reaction is a term we use to refer to this idea that one fission can lead to another, and so on, one after the other. So typically what you get, if you had a block of uranium with lots of different, lots of uranium nuclei, you would get, one fission causing, and then these neutrons would then go on to cause more other fission events. And you'd get this increase in the reaction rate, because with every fission, you get 2 or 3 more neutrons, which can then multiply the reaction rate. So the problem is, or one potential problem is, that very quickly the reaction rate would get out of hand, right? Because you might be able to see that potentially you could have one fission event here producing 3 neutrons, so therefore causing 1, 2, 3 more fissions, and then each of those would produce 3. So then you'd have 9, then you'd have 27, then 81. So you could quickly get this runaway reaction rate, which can be useful, right? If you want to destroy large swathes of a city, it can be useful to have a chain reaction like that. But what we are most interested in is how you can control a chain reaction to produce energy which is usable. Anything left to say about this reaction? Well, there is one other thing that's produced, which I haven't mentioned specifically, and that is kinetic energy. So all these particles have kinetic energy. So the products of fission have kinetic energy. So that's what form the energy produced is in, the kinetic energy of the products.
Is that transferred as heat? Because kinetic energy.
Yeah, exactly. So so absolutely. Ultimately, the kinetic energy that the neutrons and the daughter nuclei have are transferred to the moderator and the coolant and warm them up. So ultimately, yes, that kinetic energy is transferred to thermal energy, which is then carried by the coolant to the turbine. But this is just one diagram showing the fission process. U235. Okay, let's look at the structure of a nuclear reactor. So this is almost like a cross section, a cutaway of a reactor, and what you have are, or is, the moderator, and you can see the moderator is this kind of block which has, you know, fills the reactor space. Okay, so what I'm shading in orange is all moderator, and that the job of the moderator, you'll remember, is to slow down the neutrons produced in fission, slow down neutrons produced in fission, because that means that they're more likely to then be absorbed by a uranium nucleus, then cause more fission. So slowing down the neutrons produced in a fission, sort of instance of fission, then makes those neutrons more likely to go on to cause fission again, which is good. If you didn't have moderator, it would be unlikely that you'd get a significant reaction rate. Neutrons more likely to cause further fission. Now, when I teach this to the fourths, I always say, you know, a lot of people would expect the neutrons, the higher energy the neutrons would have, the more likely it is they'd cause fission because they're smashing the nucleus apart. But that's not what's happening. That's not what is happening. What's happening is a uranium-235 nucleus is just sitting there, and then it has to absorb the neutron as the neutron goes past. And that is more likely if the neutron's moving slowly rather than moving quickly. So that's why slowing down neutrons is good. It gives the uranium more chance to absorb them. So the moderator fills the reaction space, the reactor core. And hopefully you can see through the moderator, you've got these coolant pipes, which are usually carrying water. So water is the coolant typically, and this ultimately transfers energy from the reactor core to the generator. Okay, because usually, in fact, always in a power station, whether it's coal, oil, gas, nuclear, ultimately to generate electricity, you have to make a magnet or spin near a coil or vice versa. So ultimately you use the coolant to drive a turbine, which then makes the generator spin. So that's what the coolant does. The fuel rods, well, that's easy. The fuel rods you generally put in and leave there. They contain the fissile nuclei, or if you want to just call it the nuclear fuel, you can, i.e. uranium-235. Usually it's probably in the form of a compound like uranium oxide or something like that, rather than pure uranium metal. Finally, well, not quite, but almost, control rods, they can be taken in or out, so they can be adjusted. And what the control rods do is absorb neutrons. And what that does, it allows you to control the reaction rate, allows one to control the reaction rate. Because if you say you removed all the neutrons, absorbed them all, sucked them all up, or just absorbed them, you wouldn't be able to have more fission occurring. Okay, so you could in an emergency, insert the control rods fully, absorb all the neutrons, stop the reaction. Typically what you want to do is to try to have the control rods in, so only, you absorb like excess neutrons, so maybe only allow 1 neutron, right, per fission event to go on to cause a further reaction, because then the reaction rate doesn't multiply every time. Once you've got a reaction rate you're happy with, you can absorb like maybe 2/3 of the neutrons to keep the reaction rate going at a constant rate, but not growing exponentially. So typically, what you need to know is ultimately that control rods absorb neutrons and allow 1 to control the reaction rate. Examples of materials used, control rods, you will remember, are either boron or cadmium. They're elements. And for the moderator, the typical materials are graphite. And there's another thing called heavy water, which is it's basically water where you've got, instead of H2O like that, you've got water with a heavy isotope of hydrogen deuterium. So it's literally water, but with a heavy isotope of hydrogen. Heavy water. Okay, the shielding obviously blocks ionizing radiation from escaping. Ionizing radiation and nuclear material from escaping the core. So it'll be usually it's kind of lead, e.g. I mean, to be honest, it's going to mainly be concrete. So usually meters of concrete are used, but you could use lead as well. Okay, so that sort of summarizes the different parts of a nuclear reactor. So any questions on any of that?
No.
Okay, fusion. So fission is splitting of the atom, large nucleus, splitting into 2 smaller daughter nuclei, energy produced. As it turns out, you can also generate an energy by this process, fusion, which involves basically taking 2 smaller nuclei, allowing them to join and forming a larger nucleus. Okay, so for instance, you might take, hydrogen, 2 hydrogen nuclei, and then you might form hydrogen 2. And you might also have other products. The detail of a fusion reaction, as in the equation, you don't really need to worry about. What you need to appreciate is that it's the fusing of 2 nuclei which create a larger one and that gives out energy. What's important to note is this bit. It is difficult to do as the nuclei repel each other. And the reason for that is that nuclei are both, or all nuclei are positively charged. So when you bring them close together, they exert a force on each other, a repulsive force, which gets larger and larger the closer they get. What that means is, in order for them to actually come into contact and join, they need to have a very high velocity to overcome the repulsive force. And this is what has been written here. Nuclear repulsion requires high speeds. Now, you will know, because you did this recently, that a high average molecular speed or nuclear speed, right, high particle speed, translates into very high temperatures. So in order to cause fusion or create, stimulate fusion to occur, you need very high temperatures. And I'm talking temperatures of the order of 10 to the 6 Kelvin. So we're talking millions of Kelvin, probably more than that, more like 10 to the 7, 10 million Kelvin in order to initiate fusion. So it's very difficult to accomplish, certainly on Earth. Obviously it happens all the time in the universe because stars produce energy via fusion, but those temperatures in the middle of a star are caused by, ultimately it's by gravitational infall of material and potential energy being converted to kinetic energy, and that ultimately, because it's such large amounts of matter conglomerate, it means the temperature gets very high and fusion can start. On Earth, we can build fusion reactors. The difficulty is containing a piece of matter which is 10 million degrees Kelvin in temperature. So you need to use magnetic fields. You can see these are Dr. Marlowe's notes I've stolen. You can see that magnetic fields, you need to keep the plasma, which is the highly hot hydrogen gas, which has been ionized, away from the walls of the reactor. So you need to sort of control it and keep it away from all the walls. The only way to do that's with magnetic fields. So it takes a lot of energy, first of all, to raise the temperature of the hydrogen, but also a lot of energy to energize the magnets, which control the sample. You don't need to worry too much about all these advantages and disadvantages. I don't think they're on the syllabus, but they're there if you want them. So headline points: fission, splitting of a large nucleus into two smaller ones; fusion, joining two small nuclei to form a larger one. Again, the energy that's produced is kinetic energy initially, but then obviously that can be transferred in a similar way, perhaps using a coolant to drive a turbine. So that more or less covers fission and fusion. Let me check the checklist for fission and fusion. So we've talked about fission, fusion, describe the process, daughter nuclei, small number of neutrons, chain reaction, control rods moderator, shielding, difference between fission and fusion, that's obvious, splitting versus joining. Know that fusion is the creation of larger nuclei accompanied by the release of energy. Know that fusion is the energy source for stars. Explain why nuclear fusion does not happen at low temperatures and pressures. We've said that sort of in reverse, right? You need high temperatures to get the nuclei to actually collide and join together to overcome the electrostatic repulsion. This little detail here, resulting in loss of mass. Let me just say something about that. If in any physical system, if energy is produced afterwards, right? So I've just said that this energy here is produced in the reaction. That has to come from somewhere. You can't just create energy out of nowhere. And actually what happens is the total mass of these, so the mass before, is higher than the total mass of these things afterwards. So actually what happens is mass gets converted into energy. So this energy is basically equivalent to the mass difference between the reactants and products. And this equation, which relates mass in kilograms to energy in joules, is how you would calculate the amount of energy given off in fusion. So that's one use of that rather cliched famous equation. Okay, so that's fission fusion. I would highly recommend that you watch the video that I sent you a link to, because what you can do then is you can rewind it, watch it back, and watch it at your own pace and write notes as you go. However, I am happy to spend some time now answering questions, if you have any, on radioactivity. So let me put the checklist up here. Now, you covered this year, so to be honest, I suspect that a lot of this is still okay. So any questions, fire away. If you want to leave, you can. I mean, this is just
the one question I have, sir, is 7.15. I don't think I know.
okay. So,
or it might just be how it's been
no,
phrased.
sometimes, you know what? Sometimes well, not this year, but the year before, I forgot to actually cover this, because this was actually an addition to the syllabus in 2018, I think. So some beaks might have neglected to cover it properly. Anyway, what's the difference? Imagine I had an apple, right? And I had some uranium or some radioactive source here that was emitting radiation. Let's say it was beta. Now, this beta radiation, which was incident on the apple, that might cause damage to the apple, right? It might cause some of the apple's atoms to become radioactive, to become charged, right? It might ionize them. Okay, so you might end up with some of the atoms on the apple becoming charged, right? Because the beta particles would cause ionization. So then if you took the beta particle source away, what you'd be left with is an apple with some ions inside it. You would say that that apple has been irradiated because it's had radiation incident on it, which might have caused some ionization, but none of the apple is actually radioactive itself. So none of the atoms within the apple are radioactive. The apple is not emitting alpha, beta, or gamma, but it has been irradiated. Compare that to a situation where you take the apple and then actually add to the apple, like, you could like dig a hole in it or stick to the outside of the apple some radioactive material. So if this is some radioactive material, now the apple would be being irradiated, sure, because there'd be radiation coming from the radioactive material. But because now the apple has got some radioactive material sort of on it or inside it,
It'll continue, right?
Then you would describe it as contaminated, because now there is radioactive material present. Whereas if it's just been irradiated, there's no radioactive material present afterwards.
Okay. I assume you could eat the irritated one, you couldn't eat the other one.
Yeah.
So
the irradiated apple would be safe to eat, absolutely. So Snow White could eat the irradiated one. Whereas if you wanted to kill someone or damage someone, then you'd give them a contaminated apple. So then they'd take radioactive material inside of them.
Okay.
So yeah, that's the difference.
Okay, thank you.
All right. What else could I do? Okay, since there are no questions, let me take this one. So let's talk about a Geiger-Müller tube just for a minute.